Hi students, welcome back to Wisdom Academy YouTube page. In the previous video, you have learnt about energy stored in a capacitor, you have learnt about redistribution of charges and common potential. In today's video, we are going to see about polarization and susceptibility. Polarization is a concept where students confuse a lot. So please see this video with a lot of seriousness. By the end of this video, I hope you get a clarity over polarization. So first I will talk about dielectrics to you and how dielectrics behave when they are kept in an electric field. So let me create one electric field here. So how electric field is created? By keeping two plates, one of positive charge and another of negative charge. Suppose there is an electric field which is moving in this direction, and in this electric field I keep a conductor. I have a conductor here. This is the conductor material. So I think I have already told you behavior of conductors in electric field, and there if you remember what I told you, I said you whenever a conductor is kept in electric field, the net electric field inside this conductor becomes zero. And why? What was the reason? Because there will be an electric field induced inside this conductor in such a way that this plate will acquire negative charge and this side you will start getting positive charge. So there will be one opposite electric field produced. Suppose this is the value of E, then I will have E induced in the opposite direction. This is the E induced, and E induced will keep on increasing up to it reaches the value of E applied, and one point will come where E induced will be equal to E applied, and at that point the net electric field will become equal to 0. So what happens whenever a conductor is kept in an electric field, the net electric field of the conductor becomes 0. But this is not the case in the case of insulators, or we call it as dielectrics. When dielectrics are kept in electric field, the electric field does not become 0, but the electric field gets reduced. I will tell you how. So let us suppose there is a electric field, and inside this electric field I place one insulator or dielectric, you can say whatever you want to say. What happens in the case of dielectric? There is definitely some electric field produced, but not as much as what is produced in conductor, and this electric field whatever is produced will never be able to reach the applied electric field. So here the E induced becomes equal to applied electric field, and that's why the net electric field becomes 0. But in the case of insulator or dielectric kept in an electric field, the net induced electric field on this dielectric will never reach the value of E, and it will just reduce the value of electric field, does not make it 0. So what happens? Suppose I have the net electric field in this direction as suppose some 10 units. I get 3 units of induced electric field, then it will cancel only 3 parts, remaining 7 units of electric field will still be there. But what is it doing? It is reducing the electric field. So what you came to know, whenever we keep an insulator or a dielectric inside an electric field, it reduces the electric field. Now how it is helpful to us? You know very well what about the capacitance. So capacitance is what is capacitance? We know that Q is equal to C into V. So what is C? C will be equal to Q by V. So we know that capacitance is inversely proportional to electric potential, and you know what is potential also? It is E into D, that is distance. So capacitance and electric field are inversely proportional. As the electric field will reduce, the capacitance will increase. This concept we use to increase the capacitance of the capacitors. So when we introduce a dielectric inside a capacitor, it will enhance its capacitance. So before going to this part, how the capacitance value changes for a capacitor when a dielectric is kept inside that, I am going to talk about something called as polar and non-polar molecules. So dielectrics are of mainly 2 types. One thing is non-polar molecules and polar molecules. So I will talk about this non-polar molecules and polar molecules, how they behave, what is the difference between them. These things you would have also studied in chemistry, but I am going to just recollect it. So if I talk about any non-polar molecules, generally non-polar molecules are diatomic molecules like hydrogen, like oxygen, and polar molecules, the best example can be HCl, it can be carbon dioxide, and ammonia, we have methanoic acid, many things are there. So let us take example of hydrogen. So what happens in hydrogen? There are 2 atoms of hydrogen in a hydrogen molecule. What will happen if you see the positive space of this hydrogen, it will be in the center, and positive space of this hydrogen, it will be in the center. Electron will be somewhere that we can find only by the probability distribution, but somewhere it will be there, and here also somewhere it will be there. The net positive charge of these two atoms, if I try to find, it will come somewhere in the center of this line, join the two positive charges. So, the net positive charge acting on this particular hydrogen molecule will be somewhere in the center of the line joining the two positive charges. Similar way, if you find the net negative charge, it will also come at the same point. So, net positive charge and net negative charge, it comes at the same point for any non-polar molecules. Even in the case of oxygen, same thing happens. We take two atoms of oxygen, their positive charge and negative charge center comes at the same point. So, what happens in the case of non-polar molecules, the positive and the negative centers are at the same point. If they are at the same point, will there be any dipole moment? Definitely it will not be there, because for dipole moment they must be distance apart. You know what is a dipole? Dipole is a arrangement of equal and opposite charges separated by a small distance. There is no separation between the positive and negative charge, so there is no dipole moment. Here there is no dipole moment. Or I will say it is not a dipole, it is a non-dipole. But if I take any polar molecule, for example, if I take HCl, so there is a huge chlorine atom and there is a hydrogen atom. What happens? Chlorine, you know from knowledge of chemistry, it is very electronegative in nature. So, if you, first of all, when you see their positive centers, the positive centers will be somewhere here, and being more electronegative, the negative center will be more towards here. Let me assume it to be here. So, if you see, the negative center and the positive center of this molecule are not coinciding. If one is here, if I draw it separately, one is here, that is here. So, what it forms? It forms a dipole, similar to carbon dioxide also. So, what happens? I should not say carbon dioxide, I will say ammonia. I think carbon dioxide comes in the non-polar nature. So, polar molecule, if I am saying, what happens to any polar molecule? The center of positive charge and center of negative charge are not at the same point, and they have a small separation between them, which creates a dipole moment, and it acts like a dipole. So, what is the major difference between a polar molecule and non-polar molecule? Non-polar molecules will have no dipole moment, whereas polar molecules, they will have dipole moment. Now, let us see how this non-polar molecule dielectric and polar molecule dielectric behave when they are kept in an electric field. So, suppose I have a particular element which is made up of purely non-polar molecules. So, all are non-polar, that means their positive and negative centers are at the same point. So, what will happen? What will be the net dipole moment in this case? The net dipole moment will be 0, isn't it? Why it will be 0? Because we know that dipole moment is equal to q into 2d, and since 2d is equal to 0, this p also will be equal to 0. It is very simple. But this element, when it is subjected to electric field, then what happens? Let us see. So, now what I am going to do, the same element I am going to put it in the area where I have a electric field. So, when I have an electric field and I keep this non-polar element, then their positive center, see this is when this is the direction of electric field, we can understand that here there are positive charges and here there are negative charges. So, what will happen? The positive center of this polar molecule will start getting attracted towards that negative, and negative will start getting attracted towards positive. So, it will start forming something like this. So, all their polar molecules, non-polar molecules start turning into polar in nature. So, can you feel what has happened? When an element with all non-polar molecules is kept in an electric field, then now will the net dielectric moment be equal to 0? It will not, because there came some distance between the two dipoles. So what happens whenever a non-polar molecule is kept in an electric field, then its dipole moment starts to increase. And if I further increase the electric field, then the separation will further increase and it will have more dipole moment. This is a case where the electric field is further increased. So I can write like this. This is E2 and this is E1. When E2 is more than E1, then P2 will also be more than P1. The net dipole moment is increasing. Obviously, it will increase. Why will it increase? Because the separation between them is increasing. And I told you the dipole moment is linked with the separation between them. Separation is increasing, dipole moment will increase. Let us see the behavior of a polar molecule element when it is kept in electric field. So suppose I have an element made up of polar molecule. So polar molecules are something like this, which are oriented randomly here and there. So if you see the dipole moment direction, it is from negative to positive. It is like this, it is like this, it is like this, it is like this. So what is the net dipole moment of a polar element without electric field? So when there is no electric field also, what is the net dipole moment? Is it 0? It will be 0. Why will it be 0? I will tell you. The net dipole moment will be 0 even of a polar molecule, arrangement of polar molecules. The reason for that is, see, it is randomly united. One thing is like this, another thing will be like this. One thing like this, another thing will be like this. So they will cancel out each other and the net dipole moment again becomes 0 for an element having all the polar molecules. What happens when you keep this polar molecule element in a electric field? So now I have electric field and I place this element inside this electric field. What happens when you keep a dipole in an electric field? You studied in the previous chapter, it will experience a torque. The torque will start rotating it. So this negative, so suppose I have something like this electric field. So you will find that this negative will be going this side and positive will come this side. This negative will go this side and this positive will come above. This positive will go this side, negative will come above, negative will go this side and positive will go this side. So all these things will start getting oriented. In what fashion? In a way that all the negative positive accumulated like this, negative positive, negative positive, negative positive, negative positive. So the net dipole moment definitely is not equal to 0 and is aligning itself in such a way that it gets some net dipole moment. Not only that, further same way if I increase the electric field, it will further improve the orientation and it will perfectly come as a dipole. And if you see the net dipole moment, that will further increase. Definitely not equal to 0, and if it is P2, this is P1, then P2 become equal to greater than P1. So what we are coming to know, if you place a non-polar molecule or a polar molecule, there will be some net dipole moment when there is electric field passing through it, and when the electric field is increasing, the net dipole moment also will increase. We came to know that whenever a polar or non-polar molecule is kept in an electric field, then there exists some dipole moment. Now suppose I give you an element and I say what is the net dipole moment of this element. It is very difficult for you to find. The reason is how many dipoles it has, we don't know. That's the reason we come to a new concept where we will talk about dipole unit per unit volume, dipole moment per unit volume. So suppose I divide into this thing into 6 parts, I can say that this part has one dipole. So I will come to one dipole moment. So I will come to a concept of dipole moment per unit volume, and dipole moment per unit volume is also known as polarization, capital P. So what is polarization? It is net dipole moment per unit volume of any element. It is polar element or non-polar element. So what is polarization? We came to know that polarization is dipole moment per unit volume. Now we found that this polarization is directly proportional to electric field. The more is electric field, more is the polarization, less is the electric field, less is the polarization. Already we have seen as electric field will increase, dipole moment will increase, as dipole moment will increase, polarization will increase. So since polarization is directly proportional to electric field, To remove proportionality, I have to add a constant, and that constant is called as, chi, a Greek word, chi, chi. Chi, E I will write, and that is called as electric susceptibility. Electric susceptibility. So I am very careful. I have used the word electric before the susceptibility because there will be something called as magnetic susceptibility also coming in the next chapter. So please remember that chi or electric susceptibility, I can write from here, this will be equal to polarization per unit electric field. Now, is polarization a vector quantity? Of course, because dipole is a vector quantity, this will also be a vector quantity. Is electric field a vector quantity? Very well, we know it is a vector quantity. So, we can say that electric susceptibility is polarization per unit electric field. After we have learnt about dielectric and how it behaves when it is kept in an electric field, what we have understood? We have understood that whenever a dielectric, it is placed inside an electric field, then what happens? So, suppose this is the applied electric field, then there is a polarized electric field coming on this, which will have the opposite direction, and definitely this polarized electric field will not be as much as applied electric field, so it will not be able to cancel it out, but it will reduce the electric field inside the capacitor, isn't it? So, suppose I am writing EP as the polarized electric field which comes inside the dielectric because of the negative and positive charges. I can write what is the net electric field remaining on the dielectric, that will be equal to E naught minus EP. So, this is the electric field which will remain inside the dielectric, and why it remains in the dielectric? Because some of the electric field will get cancelled. I just said before some time that suppose I have 10 units of electric field, then suppose 3 units is cancelled by this polarization, then this will be 7 units left. So, the direction of the electric field inside a dielectric will obviously be in the same direction as that of E naught. So, already I have discussed about dielectric constant, also called as relative permittivity, in the first chapter. There we told the relative permittivity is epsilon r, it is also represented by K. So, both are correct. Even if you write epsilon r, it is also correct. Both have same meaning, dielectric constant or relative permittivity. So, what we have come to know, there if you remember, I told relative permittivity is equal to F by F naught, isn't it? Or I will say it as like this, F naught by M, F. What is relative permittivity or dielectric constant in terms of electric field? It will be E naught by E. So, again this how I wrote this, F is equal to Q into E. So, Q will get cancelled. So, here E naught will come, here E will come. What I mean to say, this dielectric constant, which can also be written as K, that is equal to electric field applied by the electric field present inside the dielectric. So, I can write further it to be E naught by E naught minus EP. So, we have come to know that dielectric constant is equal to applied electric field by electric field present inside the dielectric. So, I mean more than remembering this formula in terms of E naught and EP, you can just remember like this: dielectric constant is equal to electric field applied by electric field inside the dielectric. This is the concept, right? Now, what is dielectric strength? I have even talked about dielectric strength when I talked to you how to charge a capacitor. So, dielectric strength, there I talked in context of the charges being sent inside the capacitor and the air present outside is getting polarized, and one point came when the breakdown voltage reached, and the air molecules, they broke up and electrons started getting neutralized with the protons present, and then we got some kind of ionization of the field. I talked about that. Same thing. So, what is dielectric strength? It is the strength of any dielectric before it attains breakdown. Now, what is the meaning of this? See, I told you that inside dielectrics we will have dipoles. Suppose there is a dipole which is negative and positive in nature. Just now we have discussed, as the electric field will increase, this dipole will start getting apart from each other. There will be a limit for that. So, one time will come when it will break. It will break and electrons will go on this side, protons will go on that side. That voltage is known as breakdown voltage, and the strength of this dielectric to not before reaching the breakdown voltage is known as dielectric strength. So how I define dielectric strength? It is the strength of any dielectric before it loses its insulating property at the breakdown voltage, right? So why it happens? It happens because as the electric field is increased, the dipole moment also is increased, or I will say the distance between the charges also increase. A time comes when the charge gets separated from each other and behaves as individual charges and not as a dipole. So that is called as dielectric strength. We have already learned that the capacitance of a parallel plate capacitor would be epsilon naught A by D. Now I am going to see what happens when you place a dielectric inside a parallel plate capacitor. There is a parallel plate capacitor, something like this, having positive charge on one plate and negative charge on one plate. So there will be an electric field between them. Let this electric field be E naught. So what is the initial capacitance? Initially I can write the capacitance C naught will be equal to epsilon naught A by D. Also the electric field inside this plate, that will be equal to sigma by epsilon naught. We have learnt about this. What is sigma by epsilon naught? It is the electric field inside the two charged plates, equal and opposite charged plates. So if I further on to write, I can write even as Q by A epsilon naught, because we know sigma is equal to Q by A. Let us introduce a dielectric medium between them. So I am introducing one dielectric medium of thickness T. Let the thickness be T. Initially the thickness of this capacitor plate or the distance between two plates was D. That's why I have written as here as D. Now I have introduced the dielectric with thickness T. Now what will happen? The moment the electric field is there and you introduce a dielectric, like I said you, there will be a polarized electric field started to come. That will be EP, and it will cancel out some amount of E naught, and what will be left inside this dielectric will be E, which will be equal to E naught minus EP. Just now I have talked about that. So this will be the electric field inside the dielectric. So if I want to write that, I will write like this. So electric field inside dielectric, that is equal to E, and that will be E naught minus EP. Fine. Just now before some time I have told you the dielectric constant K is equal to E naught by E naught minus EP. From here I can write E naught minus EP is equal to E naught by K. I will put this here in this equation and I will get E is equal to E naught by K. That is applied electric field by dielectric constant. Now if you see, the potential in this dielectric slab will be equal to electric field into this thickness T, and in the remaining distance there will be a potential that will be equal to E naught into this thickness D minus T. So I will write the total potential, that is equal to V, and that will be equal to what? That will be equal to E naught into D minus T plus E into T. That is, this is the, we know that V is equal to E into distance. So applied electric field into the remaining area plus electric field inside the dielectric into thickness of dielectric. So now if I write E naught D minus T, and what is E? E is E naught by K, E naught by K into T. So from here I get E naught, if I take common, it will be D minus T plus T by K. This is the formula of potential, electric potential, which is totally present for the system. Now I want to find the capacitance of this thing. So what will be the capacitance? We know capacitance C is equal to Q by V, and what is Q? Q is sigma into A, or sorry, sigma is equal to Q by A. So Q will be equal to sigma into, am I right? So it is equal to sigma into A divided by V. V is E naught into D minus T plus T by K. Now what is E naught? From this equation we know it is Q by A epsilon naught. So I can write C is equal to sigma by A divided by, I can write like this, or I can write from here sigma by epsilon naught. So sigma epsilon naught O will go above and it will remain d minus t plus t by k. Sigma sigma gets cancelled and I get the capacitance, new capacitance when this dielectric is introduced as epsilon naught A by d minus t plus t by k. So, what we have understood? We have understood that when there is a dielectric present inside a capacitor, then the capacitance of the capacitor will be changed as epsilon naught A by d minus t plus t by k. In the previous case, when I talked about the capacitance without this dielectric, it was epsilon naught A by d. So, now I will tell you one thing. Suppose this dielectric present is completely occupying the capacitor. Now I have kept off thickness T. So I am talking about the point when T becomes equal to D, right. This will happen if the dielectric is completely occupied in the capacitor. If I want to draw a diagram will become like this. This is the capacitor and it is completely occupied by a dielectric. Now let us see what would be the capacitance in that case. So capacitance will become equal to epsilon naught A divided by D minus D plus D by K. These two will get cancelled. So what I will get, C is equal to epsilon naught K A by D. So this will be the value of capacitance when it is completely filled by the dielectric. One more thing you can find from here. Suppose there is no dielectric, that means T is equal to 0. So when T is equal to 0, let me write it here. When T is equal to 0, then what will happen? Let put T is equal to 0, this will become 0, this will become 0. So I will get capacitance is equal to epsilon naught A by D. Isn't it same as this? So better than remembering the capacitance of a capacitor without dielectric, remember with dielectric, and as per the situation, if there is the capacitor without dielectric, then put T is equal to 0. If capacitance is filled with dielectric, then put T is equal to D. And if there is some dielectric of length thickness T, then this is the formula. This formula can help you to derive any other formula. So what I will say, preferably for remembering the capacitance of any parallel plate capacitor, the formula to be remembered is epsilon naught A by D minus T plus T by K, where epsilon naught is the permittivity of free space, A is the area of the plate, D is the separation between the two plates, T is the thickness of the dielectric, and K is a dielectric constant. So with this we come to an end of this chapter. So in this chapter we have learnt about electric potential, we have learnt what is potential and what is potential difference, we have learnt about what is the electric potential for a single point charge or for multiple charges. We have even found the electric potential for a dipole at an axial point, at an equatorial point, also at a general point. Then we talked about relationship between electric field and electric potential. We also saw what is equipotential surfaces and what are its properties. We talked about conductors and the conductors inside the electric field, and then we learnt about capacitors. We learnt about capacitors in series, capacitors in parallel. Then we learnt about energy stored in the capacitor, redistribution of charges and common potential. And in today's session we have learnt about dielectric and what will be the capacitance if dielectric is introduced inside a capacitor. Why we introduce the dielectric in a capacitor? To increase its capacitance, because I have told you, as you introduce a dielectric inside the capacitor, the electric field will reduce. As the electric field will reduce, the potential will reduce. As the potential will reduce, the capacitance will increase. So with this I come to the end of this chapter. In the next video I will be solving some numericals based upon it, and I will definitely take all the unsighted numericals. So please study well. We are going to start a third chapter. I hope you are following and you are studying and doing all the numericals at your home. Only then it will be helpful for you. So with this I am winding up today's video. Please like it, share with your friends and subscribe our channel. Thank you.